Right. So the big question is, as I mentioned, do small-scale loops contribute to corner heating and the dynamics of the solar atmosphere? So I will walk you through our knowledge about these small-scale loops, and I will start with a quick historical review because it's very exciting what happened. So between 1969 and 1973, the Naval Research Laboratory launched a few rockets with X-ray telescopes on board, and they decided for each launch to select a different exposure time. At that time, the region, outside active region of the sun, were very homogeneous, nothing was visible in this region. So that's where the quiet sun term comes from. So on April 8, 69, they used a very long exposure. And when the images came back to Earth, they found that actually the quiet sun is highly structured with many small-scale bright X-ray emission structures, and they named them X-ray bright point. They were randomly distributed on the solar disk. They were also found in polar regions. So this is one of the first images from this time. And in these circles, you can see these X-ray dots, which excited very much the solar community. So simultaneously, they also observed from ground the solar magnetic field, and they could notice that every place where there is this bright dot, they can find a bipolar magnetic region, so positive and negative polarity. From 1973, the Skylab was launched, and they found that these bright points, using spectroheliograms with unprecedented high resolution, 2 arcseconds, but these bright points are composed of small-scale loops. And you can see here, this is a spectroheliogram in the iron 50 line, showing these little strips. And believe me, these loops you can see here in the presence of sophisticated observations. So on the left side, you see the similar image to what I showed before, just taken at different time. And on the right side, it's written CBP. So after the UV observation started, we actually introduced the term corner bright point, not X-ray bright point. And the reason was we were observing this phenomena also in UV at lower temperatures, at 1 million and 2 million degrees, even lower. So the term corner bright point was introduced, and the definition, it describes small-scale multi-loop system in the solar atmosphere. You will hear later how high in the solar atmosphere, which appears with enhanced emission. But as I mentioned before, around these bright loops exist also very faint loops, and they form the background emission or the background of the solar atmosphere when the active regions are not present. So here I will show you one very exciting movie. On the right side, you see magnetogram. On the left side, image taken with the AAA, the Atmospheric Imaging Assembly, and it samples plasma at 1 million degree. And this movie, on the right side, you see magnetic flux emergence from the convection zone. On the left side, you see the bipolar region and bright emission from small-scale loops. It gets more exciting, just wait, and comes another region close to it. This is a movie covering 48 hours of observations with a cadence of six minutes. So this happens continuously on the sun, in all regions of the sun, outside active regions. And this is a faint loop. A nice example of the faint loop is flickering over time. These loops are very stable. Typically, they connect magnetic polarities which are far away and which have very, very, very long time. They are hard to distract due to solar convection. So let me talk about morphology and size of these small-scale loops. The appearance of these loops in solar observations depends on the resolution of the instrument and depends on the temperature which is sampled by this instrument. So in Skylab time and later Yoho, this is the Japanese mission, in X-rays and the ultraviolet imaging telescope on board the Solar Heliospheric Observatory, they were seen as little diffused cloud with bright core. Later, came the TRACE mission, a small rocket American mission, and they could find the individual little loops. It was very exciting time investigating the evolution of these small scale loops. And then we have more observations. The latest one, the best resolution observations in the solar corona come from the EUI imager, the high resolution imager on board the Solar Orbiter mission. Shadia Habal and co-authors in 1990 using spectroheliograms, and these spectroheliograms actually were taken with during the Skylab mission, found that coronal bright points, I will use this term through my talk, are composed of loops at different temperatures. So they had, however, just spectral data, so they could see emission in transition region, in chromospheric line, also in coronal line. The height of these loops, as I mentioned, this is low corona, and these loops, when flux emerges, as you showed you in the movie, when flux emerges, they are as small as 3.5 megameters. This is tiny, tiny loop, but still the plasma is heated to coronal temperatures or to 1,000,000 degrees in this loop. They grow to reach up to 60 arc seconds or 43 megameters. However, sometimes we observe a very, very, very large loop system in the quiet zone. They are not active region, and they have a very, very long time. Typically, at the end of lifetime of these small scale loops, when the flux converges and cancels, disappears, we can see again some very small loop of 3.5 megameters. As I said, height, these loops are found with the coronal loops are reach up to 10 megameters, but they have average height about 6.5 megameters. And Dr. Kwon, now working at Kwasi and co-authors, this is during his PhD with Professor Sheff from Seoul National University, found that using stereo observations, that these loops are multi-temperature system composed of hot loops overlying cooler ones with cool legs. And most recently, during my BrainPool program work at Seoul National University, I used the FIS instrument developed by Kazi with collaboration with SNU. We found that bright point also is composed of chromospheric loop, which are seen in the H alpha line, and they reach heights at about 1.5 megameters. This is an example of these loops, and you can see here in this panel. This is line center of H alpha, and you can see these loops evolving very dynamically. This is the coronal counterpart, and these are the two polarity, negative and positive polarity, which are responsible where the magnetic loops are rooted of this bright point. And on the right side, you can see this is composed image from the blue and red wick and the H alpha line. So let me continue further about the lifetime of this loop system. Well, this loop system, when seen in X-ray, have much shorter lifetime than seen in UV. And in the past, actually, there was a little bit confusion about the lifetime of bright points, because they were saying, oh, these bright points, these small scale loops have lifetime only of 2 minutes. But actually, the reason was, and you can see in this plot here, this is the top curve, light curve, shows EUV emission, and the bottom two show X-ray emissions, so the emission from plasma at higher temperatures. And you see this little spike during the lifetime. Actually, this is in periods when microflare or flares occur in this small loop system. I will talk about these microflares later in my presentation. So they appear in X-ray for a very short period of time, it disappears. But the loop system is still there, but only it's not supported by strong magnetic field, and it's only seen in UV. In UV, the average lifetime is 20 hours, but we have seen loop system that last up to 9 days. These are typically very large coronal bright points with a diameter up to 720 megameters. Electron density. A lot of studies have been done about the electron density, and typically spectroscopic data are used with the line ratio of spectral line of the same ion. And it has been found that the electron density of this loop system are very similar to active region density. 10 to the 10th in the transition region temperature, so up to 500,000 degree plasma, and 10 to the 9 at coronal temperature 1 million degree. So the conclusion is that this small loop system are actually downscale active regions. So the sun is covered with tiny active regions, and it is believed that these active regions are created from a local dynamo. The coronal density remained quite relatively stable during the lifetime of coronal bright points, but when flares occur, they can increase up to 3 times. And this is a study by one of our Japanese colleagues when he was working at Max Planck Institute. This is a very nice presentation of the temperature structure of the bright points, and this is done with spectroscopic data from the eye spectrometer on board the Hinode mission. And you can see here with the red color, this is iron 10 line, so 10 to the 6th temperatures, 1 million degree. And this is the red color, so the bottom. So you observe the loop system upside down. Yeah? It just happened to be formed like that. You can see here with yellow the next higher loops at 1.2 million degrees and up to 1.5 million degree in the iron 50 line on top of this image. Typically, the foot points of this loop system is seen at chromospheric, so lower temperature, 10,000 Kelvin and around, and transition region up to 500,000 Kelvin. So this is the temperature structure of this loop system. And again, you can see here the H alpha loops I mentioned before that lie on the bottom, which cannot be sampled. Eye spectrometer doesn't have chromospheric line to observe. So elemental abundances. This is a nice story. When I was writing this review, I contacted Dr. Scheele, and asked him permission to reproduce one of these figures. And he was very talkative, and he told me, and so I explained him what I'm writing, and he said, oh, do you know, Maria, I have written actually a paper about photospheric abundances from data taken with Skylab, but I'm very embarrassed. And I said, why? Because when I wrote the paper, a colleague of mine said, oh, this what you see there on the sun are volcanoes. So I wrote in my paper because we were seeing emerging and forming loop systems. So they wrote in this paper that this is actually about a volcano. But now he knows that these are coronal bright points or loop systems. So I included this in this is as a first result that this loop system have photospheric abundances. Later, this has been confirmed with spectroscopic data from the UNIS mission. This is a ROCKINT mission. And why photospheric abundances? The explanation is that most probably this is reconnection driven, is because of reconnection driven evaporation. What that means is when reconnection happens in the corona, and energetic particles are guided along the field lines towards the chromosphere. The chromosphere is heated and evaporated, and therefore that's why we observe photospheric abundances in coronal bright points. So we suspect that the mechanism of formation evolution of coronal bright points is reconnection in the corona. This loop system are the host or regions of many transient dynamic phenomena. So solar wind, dynamic phenomena, we talk later about this. So spicule motos, these are the prairies of chromospheric eruption that populate the foot points of this loop system. Then, and you can see them here in this movie, these dark features, they come and go along the loops of the bright point. Microflare, I mentioned the microflare, like flares in active regions occur. So they are very they appear very quickly. The intensity in very small region increase a few orders of magnitude, and it always happens. It's believed that this is a magnetic reconnection happening along the magnetic polarity inversion line. In the quiet sun, where mostly loop system exist, we can see mini eruptions like mini coronal mass ejection. And in corner holes, these eruptions evolve. Microflares are related to jets, collimated outflow. I will show you later now simulation. But I want to show this movie showing a microflare. So you have to watch between these two opposite polarity. This is negative and positive polarity. And suddenly a brightening in the images will occur. This is a spectrometer slit. And if you watch below this magnesium line, carbon-2 line, and silicon-4 line, you see this strong blue and red shifted emission, which is a signature of magnetic reconnection happening during, which causes the macro flare. Jets, bright points are known to be the host of jets, UV, seen in UV or X-ray, so lower and higher temperatures. And this is a nice animation created by the Kinode team. These are images taken with the X-ray telescope, and you can see it's coming now, beautiful jets occurring here and here. They are highlighted now in this animation. And these jets are believed to form microstreams in the solar wind. Mini coronal mass ejection, as I said, in the quiet zone, due to the closed magnetic field, we have these bubbles like large coronal mass ejection constantly occurring, and it has been found that at least 870 occur per 24 hours over the quiet zone. And this is an example of such eruption. You can watch here, this region, hop, puff, another one, puff. And they continuously happen and are seen in various temperatures. These are transigger region, this transigger region, and coronal temperature. This is a magnetogram. Mini filament also are often related to this. So mini filament, a prominence is large. Everybody heard about this, but also there exist these tiny filaments, which are just a few kilometers long and live no more than 70 hours. And this is an example of eruption of such mini filament that causes a jet. So here is X-ray image, and you can see this beautiful eruption. These data are not very pretty. And on the bottom in H-alpha line, you can see the so-called X-ray, the flare kernels. Coronal magnetic field. For many, many years, many papers have been published about the magnetic field in the corona of bright points. And mostly they were saying that magnetic field is generally potential, but this somehow doesn't fit the picture of constantly occurring magnetic reconnection, which hits the plasma. So recently I started a project on this subject, and what I found, and this is work in progress, that the loops of coronal bright points are generally non-potential, so strong currents occur, and most probably these currents are related to continuously occurring magnetic reconnection in these loops. Oscillation in coronal bright points, I probably don't have a lot of time. Oh, I still have some time. Okay, oscillation. So emission variability is a very typical feature in this small-scale loop system. It constantly, when you see an animation I showed in the beginning, you see brightening happening everywhere in the loop system. So many works were done on oscillations, but mostly using a coronal spectral line. So lines, spectral lines form at a few million degrees, and oscillation with period between 600 and 1,000 seconds, which were explained in terms of global acoustic modes. Longer periods were also observed between 8 and 64 minutes. The most recent one is by Gao et al. 2020. And this, oh, I forgot to put here, uses AA images I showed first in my talk. They found oscillation periods which range from 1 to 8 minutes, but these oscillations were decayless, which is a very interesting result to follow. I have, however, to mention that in two of the works by Hui Tian from Japan, Beijing University, and later his postdoc Samantha et al., they have put forward doubts that some of the long period, especially oscillations, are not related to propagating waves, but most probably they represent reoccurring magnetic reconnection. So this subject is still to be explored, and the signature of propagation of waves of different kind, alpha waves or magnetoacoustic waves, needs to be investigated. So modeling, as the new solar missions and new ground-based telescopes were evolving, so was evolving the modeling of these loops. And probably the solar people here will not be surprised to hear that the first person, immediately after the first observations of these bright points were available to provide a model, was Eugene Parker. So Parker Solar Probe, which is now very close to the sun. He made a first model in 1975 and was followed by many other models. But I will mention the most recent one. And also I will mention it because this is closest to quite realistic model. Why? So there are two two codes in solar physics which produce radiative 3D MHD simulations, and these are the most realistic simulations of the sun. They cover the region from the convection zone below to 18,000 kilometers and above up to 100 kilometers. Only the quiet sun, because otherwise they are very expensive to be run. And these simulations, this is one of the codes, Bifrost simulations by a group in Spain. They did these simulations, but what is important in these simulations, they use the driver of this simulation is stochastic granular motion alone. They don't put anything artificial to push the loops so that the reconnection can take place. However, they impose the so-called magnetic null point in the corona, where the magnetic reconnection will happen and the plasma will be heated. Still, this is one of the most recent and most successful simulation of coronal bright points on small-scale loops. So about energetics, so do this loop system provide the necessary heat, at least at this height of the solar atmosphere, so that that we can register the high temperature plasma? Well, very limited observational works have been done. And the reason is, it's very complex work. So the first work was done in the 90s by Shadia Habal and Vitpro. I didn't mention here. They said, well, probably these bright sources provide 20% of the heat, but I have also to mention that the energy loss needed, so the quiet sun is heated constantly, remain at coronal temperatures, is 310 to the 5th ergs per cubic centimeter per second. So it looked like in the past that 20% is not enough from this loop. Recently, another group used SDO observations, and they concluded that only 1.61% of this bright feature. But I bring you back to this image and have a look here. So what they counted in the last study, they counted only these bright sources, but they ignored all the rest fainter loops, which are constantly there. And we measure plasma at a very high temperature. So this needs a high reevaluation. And why I say this, recently I received from a colleague, Matthias Rempel, results of his most recent work. This is the startup code, the newest code he developed in 2017. And what he concluded is that the quiet sun and open magnetic flux provide the necessary energy loss to hit the corona to 1,000,000 degrees. And I will show you these simulations, which I'm privileged to have even before the paper was accepted on 3rd of October. So, and this is, they simulate, these are observations, they simulated observations from the Solar Dynamic Observatory. And you can see here the quiet sun with numerous loops. You can see even my little eruptions in the observations. So we shared each other data, and we were so excited, said, oh, you stole my images. And no, you stole my images. So it was really, you can see that in solar physics, we go further and further in, and we are able to reproduce to large extent the solar atmosphere. Contribution to the solar wind. Well, I just will mention a work by Neugebauer and Sterling, where they speculate the so-called switchbacks. Everybody maybe heard, it was all on the news that Solar Parker probe observed the so-called switchbacks, where the magnetic field is seen to tilt us expanding from the sun. And they speculated that these mini eruptions, these jets I showed you, are the source of switchbacks. Lionel et al. 2016, they modeled jets and tried to see whether they have contribution to the solar wind, but they used jets only, very old statistics, which samples jets only corner holes, but not in the quiet sun, and then concluded that these jets do not really provide a large contribution to the mass and energy content of the solar wind. So just 0.4 to 3% mass and 0.3 to 1% energy. Well, I'm on my last slide, so I mentioned many time. So what I talked about are these small-scale loop systems, which appear to be really very important. They have been studied since 1969, so almost more than 50 years. They have very similar property as active regions, but they're all on small scale. So we have numerous small active regions on the sun, flares, eruptions of filament, magnetic reconnection, coronal mass ejection jets, but all mini, observed in relation to coronal bright points. So why they're important? Well, one of the reasons they also are important, they may help us understand how plasma trapped in magnetic loops is heated to 1,000,000 degrees. And why? And how energetic events are generated. Why? Because there is one advantage comparing to active regions. They're very simple. Most of them are very simple, while the active regions are extremely complex. They have short lifetimes, so they can be observed from birth to death. And as I said, much less complex than active region. But we have limitations and challenges using and analyzing this data of small-scale loops. Is we still have limitation of the spatial resolution. We still have a lack of vector magnetograms, which are very important for data-driven modeling in the quiet sun. But last, there is hope. And the hopes are these instruments. So we are talking about DKIS. This is the largest ground-based telescope on Hawaii. We have the FIS instrument developed by CASI and SNU, Big Bear Observatory, which I started observing now very much. We have the Swedish telescope instrument CRISP. We have the IRIS spectrometers. These are very high resolution, high cadence instrument. We have Solar Orbiter. We have a forthcoming MUSE mission. This will be spectrometer on a small mission like the IRIS mission, and it's developed by NASA. We have the Solar Sea. This is a collaboration between JAXA, driven by JAXA, ESA, and NASA. And last but not least is the DCA-L1, and this is the India Space Research Organization mission, which is coming in 2022. So this was my talk. I would like to thank you very much for your attention, and I'm very sorry for the technical glitch. Thank you.
Thanks for this nice presentation. Are there any questions?
So I have a question. So does the CDP have a cusp and sheet-like structures above the small loops?
Do they have
Cusp and sheet-like, current sheet-like?
Yes, they do. They do. I have a movie of such thing, but I have to. I can show you later. I have a movie which shows exactly this helmet structure. That's what you mean, like helmet structure above, which suggests that there is. I have actually also modeling data work on this subject, where null point is often found above this helmet streamer. So the reconnection happens there, and through heat conduction, the low-lying loops the heat is driven along the low-lying loops. So there is. This has been observed, it's always observed in corner holes, but also is found very often. We have a work published with a few colleagues, theoreticians, and myself, where we find this also in the quiet sun. So this sheet structure and null point in the corona. I can show you this in the observations and in the models later, but it's not in this talk because I had to talk for 2 to 3 hours if I had included everything. Sorry.
Are there any questions? I can take 1 or 2 more questions. I'm not familiar with the social topic, but I wonder whether people actually see the development of large-scale prominence from these mini small-scale loops during the active phase of the sun. So actually, have you done, anybody done the simulation to look at the revolution?
No. No. No, not on many filaments. We have done, okay, we have done some simulations, but these are not simulations. We use the magnetic relaxation code. So to produce series of magnetograms, I can show you, I have another movie and images I can show you if you're interested, where we use this magnetofrictional code driven by the photospheric magnetic field to reproduce series of nonlinear phosphine field lines, and we see the formation of this filament. But we can never erupt this mini filament. And the reason is because it's so small scale. We resolve the reconnection side or the activity side into 3 pixels of present instruments. So numerical diffusion is just destroying our eruptive phase, but we are hoping that the new instrument will provide the KIST, they said they will provide a magnetogram with 50 to 70 kilometers spatial resolution. So then maybe we will be able to do at least this kind of simulation, but the other simulations, nobody has looked. For instance, here, they haven't looked. They may have this here, but this is very new simulation, and they haven't looked yet because this is a dark, so this shows eruption of cool material. So should be there forming a mini filament and erupting, but they didn't analyze their data. So I talked to them and they promised that one day they will find time. But yes, nobody particularly concentrated on doing this. No, there is no project, as far as I know, in solar physics.
Any more questions? There's no, so let's thank the speakers again.